Hello students, welcome to the online lecture series of St. Andrews Institute of Technology and Management, Gurugram. Myself Satyendra, Assistant Professor in ETC Department. Our today's topic of the lecture is Master Slave Flip-flops, and we will see some conversions. How can we convert one flip-flop to other? So this is a part of Unit 1st of LOC2 BCA second semester. So let's see first. In last lecture we learned about the JK flip-flops, and we have also seen that when both the inputs are 1 1 in JK, when J is equal to 1 and K is equal to 1, we were getting a racing condition, that is the output Q n plus 1 or the next state was toggling from 1 to 0, 0 to 1, racing in the same pulse, same clock pulse. When clock pulse was high and both the inputs were 1, it was racing around from 0 to 1 and 1 to 0. So it was a problem in the JK flip-flop. How we can overcome that racing? So there are basically 2 or 3 methods to overcome that. One is, if we can make the half time period t half less than the propagation delay of flip-flop. If the half time period, okay, we can make somehow it less than the propagation delay, so this racing condition can be overcome. Second is edge triggering, that is the state changes only when the clock goes from 0 to 1 or from 1 to 0, that is at the edges, when the output changes at the edges of clock, when it goes to 0 to 1 or 1 to 0. And third is master slave configuration. It is an important topic from the point of view of our semester and semester exams. Okay, so how we can implement a master slave flip-flop? We are in this circuit, as we can see, we are using 2 JK flip-flops connecting back to back. Okay, so and the difference is that the one, that is the master, this is the master flip-flop, master JK flip-flop, and this is the slave. So this flip-flop is working when the clock is high, and the slave is working, as we can see there, we are providing it a clock through a inverter. So this is working when the clock is low. So both the JK flip-flops will not work simultaneously. If one is working, that is, if one, there is a change in state in one, there would not be a change in state in the second. It will remain in the same state until and unless the clock goes low, and this one remains in the same state until and unless the clock goes high. So what we have done using these two different clocks, that is complemented clocks, so output changes only once during a clock cycle. By doing this, what we have done, we have forced the output to change only once during a clock pulse. If it is clock is high, only this the output of master flip-flop will change. If clock is high, the output of master will change, and if it is low, then only the output of slave will change. So what we have done, we have forced it to toggle. We have forced the race alarm condition to get converted into toggling. Here we can see in the timing diagram, this is the clock 0 1 0 1 0 1. Okay, now Qn is the output of master flip-flop, master JK flip-flop. So as we can see in the picture, in the diagram given below, the QN will change as the clock goes high. So it goes there, it goes high, and it changes again when the clock goes high again. So it changes here, and it continues to be low until the clock goes high again. So now it changes to high and remains high until the clock goes high again. So whenever the clock goes high, the output of master slave changes, as we can see in the timing diagram. Similarly, when clock goes low, as we can see, when clock go on these edges, the output of slave will change, and it remains until the clock goes low again. Okay, it remains there until clock goes low again. It changes here. Now it remains in the same position until clock goes low again there. So what we have done, we have forced the output to remain in the state until the clock goes high. So it will not race around during the pulse. It will not race around. Okay, so this is how we can overcome the racing around condition in a JK flip-flop by using two flip-flops connecting each other. Like the diagram, we can see how they are connecting. Okay, we can see that how both are connecting. We have provided the clock which is complemented of the clock given to master. We are providing it by an inverter. Okay, so this is how we can implement a master slave JK flip-flop. Now the next topic is excitation table. We have already seen the characteristic or truth table of flip-flops. Now we will see excitation table. Truth tables were basically the characteristic tables which defines the operational characteristic of the flip-flop. Okay, so and the excitation table we can find for which input combinations, or we can say how the transition take place in the states, how the state changes from the previous to next state, and for what combination of inputs. So what we will do in characteristic tables, we will first put the previous state, then the next state. Now if previous state was 0 and next state was 0, so by using the truth table we can check that if S was 0 and R was 1 or 0, the next state would remain be 0. So we have put a don't care in R. It doesn't matter R is 1 or 0. Until and unless S is 0, the next state would be 0 if previous was 0. Okay, this is how we can make the excitation table of flip-flops. So this is the excitation table of SR flip-flop. Like if it was 0 and we want the state to change to 1, so what are the possible combination of S and R? So S should be 1 and R should be 0. This we can derive from the truth table. And if the initial state was 1 and the output or next state is 0, so our inputs must be 0 and 1. Okay, if the previous state was 1 and we want it to remain in state 1, then the inputs should be R is equal to 0 whatever be the S. So if S is equal to 0 and 1, we need R to be 0, so that the next state would be 1. So this is how we can make the excitation table. That is how the transition take place from one state to another for a possible combination of inputs. So this is what excitation table do. Similarly, we can see the excitation tables of JK flip-flop here. If because only we have the state can be either 0 or 1. If it was 0, it can remain in 0 or it can change to 1. We have only 4 combinations, 4 possible combination for states. If it was 0, it can remain in state 1. If it was 1, it can remain in 1 or it can change to 0. So we have only these 4 combinations for all of the flip-flops. So if the previous state was 0, it can change to 0 and 1. If the previous state was 1, it can change to 1 and 0. Okay, so this is how we can make the excitation table of flip-flops. Here I have write the excitation table of both T and D flip-flop. So if in T you can see in T flip-flop, if the previous state was 0 and we want the next state to be 0, so we will provide the input as T flip-flop has only one input, T is equal to 0. If it was 0 and we want it to be 1, then we will provide 1. If it was 1, because as we have already seen, the T flip-flop will toggle when we provide 1. That is, if it was 0, let's say if it was 0 and we will provide the input T is equal to 1, then the state would change to 1. If it was 1 and we provide input T is equal to 1, it would change to 0. So it will toggle the previous state that we have seen in the T flip-flop and its table. Similarly, D type flip-flop, we have seen that the next state is just same as the input provided. So if we want the next state to be 1, here we can see we want the next state to be 1, we will provide D is equal to 1, and if we want next state to be 0, we will provide D is equal to 0. This is how we can make the excitation tables. So now next topic is conversion of flip-flops. How we can convert one flip-flop to other. So I have write 5 steps there. It is a very important topic in the flip-flops, how we can convert from one flip-flop to other. From the university semester exams, it is very important. So there are 5 steps. First is identify the available and required flip-flop. As I have written an example also, if we need to convert JK to D flip-flop. So first of all, we identify that the available flip-flop is the JK flip-flop and we need to convert it to required, that is the D flip-flop. So first step is identify the available and required flip-flops. Then second step is make the characteristic table for the required flip-flop. Characteristic table for the required flip-flop. In this example, required flip-flop is D flip-flop. So I have written a table. This is the table, characteristic table for D flip-flop. The third one is make the excitation table for the available, which is the JK flip-flop. So this is the excitation table which we have just seen in the previous slide. So first step is identify the available and required flip-flops. Second is make the characteristic table for required flip-flop, that is the D flip-flop. So characteristic table is nothing but can be make easily from the truth table. If input if previous state was 0 and I provide 0, then next state would be 0. If it was 0 and I want 1, then T will be 1, because as we have already seen, the next state is equal to the input provided in D flip-flop. If it was 1 and I want 0, I will provide 0. Okay, and if it was 1 and I need to remain in state 1, then I will give d equal to 1. Okay, similarly now if qn is this one and we want qn plus to be this, so we can have the excitation table as we have just seen. So this is how we combine both the characteristic and excitation table. Characteristic table is written for the flip-flop that is required, and excitation table is for the available flip-flop. Now the fourth step is write the boolean expression for the available flip-flop, that is the JK flip-flop. So we have two inputs there. We have two inputs qn and d. So qn and d, and we will write the boolean expression for available flip-flop, that is the JK. So for j I have made this k map because we have only two inputs, it will be a two variable k map, and for k I have write this. So as we can see, j is 0 1, don't care, so I will make a pair and j would come out to be j is equal to d, and using the k map k would come out to be d bar, that is complement of d bar. So this is how we can convert JK to D flip-flop. JK is the available flip-flop and we need convert it to D. So we can say J is equal to D. So input is J is equal to D and K is equal to D bar. So we will put an inverter over there. So K would be D. K would be D bar. So this is how we can convert a flip-flop into another flip-flop. Let's see one more example to understand it better. Now we need to convert SR flip-flop to JK flip-flop. So available flip-flop, our first step is to identify which one is available and what is required. So in this case, available flip-flop is SR flip-flop and the required flip-flop is JK flip-flop. So second step was to write the characteristic table for the required flip-flop. So I have write the characteristic table for the required, that is JK flip-flop. This is the characteristic table. I have to include this is the characteristic table of the required, that is JK flip-flop, and with that I have added the excitation table of SR flip-flop, which is the available flip-flop. We can see from there I have write it down the excitation table of SR flip-flop. Okay, for 0 0 it was 0 don't care, 1 0 0 1 and don't care 0. So for qn is equal to 0 and qn plus 1 0, we can see it was 0 don't care. Similarly for 0 and 1 it is 1 0. For 0 and 0 it is 0 don't care, and 0 and 1 it is 1 0. We can see from the excitation table, and similarly we can write down for all the combination. Okay, so we must learn all these characteristic tables and excitation tables which we have already seen. To convert from one flip-flop to other, we need to learn all these things. So now the fourth step was the write the boolean expression for the available flip-flop. So SR is available, so we will write Boolean expression for our available flip-flop. Since we have now three variables j, k and q, n. We have three variables j, k and q, n. So we will use a three variable k map that will consist of 8 cells. Now I have, there we can see for S the k map and for R this is the k map. So for S we will make a pair and S comes out to be qn bar into j. Similarly R comes out to be qn into k, and the next and the fifth last step was to implement the circuit. So as we can see in the Boolean expression, S is nothing but the multiplication of qn bar and j. So we will use a AND gate to implement it, and output, so S would be j multiply qn bar. This is q, this is qn bar, and similarly k is equal to, as we can see, k is equal to qn into, oh sorry, r is equal to kn multiply qn multiply k. So r is k multiply qn, which is fitted again using an AND gate. So this is how we can convert one flip-flop to another flip-flop using 5 simple steps. We can summarize these steps again. First, because it is a very important topic and the question often comes from this topic in university examination. So our first step is identify available and required, because if you change the available and required flip-flops, the answer would be certainly wrong. Second is make the characteristic table for the required flip-flop and the excitation table for the available flip-flop. The fourth one is write the Boolean expression for available flip-flop and then design the circuit according to that Boolean expression. Okay, so this is it for the lecture. Thank you very much.